Welcome, everyone, and thank you for attending today's presentation on the impact of EN 50716 on rail digitalization and advanced technologies. My name is Ricardo Camacho, and I'm a Director of Software and Safety Security Standards at Parasoft. I'm also accompanied by Arthur Higgins, our Chief Evangelist, a brilliant mind and a great friend. This is going to be a very informative presentation, but before we get started, let's go through some housekeeping. First, everybody's microphone has been muted. However, if you have questions, please enter them into the questions dialog box. You can do this at any time. Also, this presentation is being recorded and will be made available shortly after the webinar. On the agenda, I'm going to start by passing it over to Arthur, where he will be speaking about some of the exciting trends in the rail industry. Then I'll be talking about the EN 5012X standards to put things in perspective before I actually dive into the new Railway Applications Requirements for Software Development Standard, EN 50716. All right, so let's get started. Over to you, Arthur.
Thanks, Ricardo, and hello, everyone. I'm so glad to be here with you today to talk about the rail industry. Like other industries, lots of fascinating things are going on in rail, and it comes down to more customization, more automation, more personalization, and as always, a whole lot more software. So some of the trends that we see going on today at a high level are some technology trends, the addition of greater automation, of course, some big data analytics and IoT and how IoT relates to the rail industry. And we'll dive into all of those a little deeper in just a moment. We also have environmental trends driving what's happening in rail, the same way we see in automotive and aviation. The push for sustainable energy to make sure that we are reducing carbon footprints and using less energy and driving down costs while driving down pollution. And also passenger trends, making sure that things are not just environmentally friendly, but comfortable and convenient for people. The design of trains, stations, and services to meet the needs of passengers to get them from where they want to start to where they want to go with minimum fuss, in comfort, in style. And these are all important things that drive rail decisions. Now, the technology trends, as I mentioned, I wanted to go into in a little more detail. Automation. We do see increased automation, whether it's, signals or checking sensors on the trains to make sure that things are working properly, trying to reduce the frequency of incidents. We still have in the industry way too many interactions at signal crossings. And of course, over the last couple of years, there's been a couple of very high profile incidents of derails with hazardous materials, which is always a problem. And so automation can help us improve safety by reducing human error where it can. The automation doesn't get bored the way that humans do, and that's a really great thing about it. So where possible, it's good. Big data analytics, looking at deep dives into the data. What's happening? How is it happening? When is it happening? Where is it happening? So that we can better understand how to make improvements. Customer experience, again, we're using technology to make sure that people get, for example, real-time information about schedules, delays, service alerts, and things like that, so they know how to show up on time and whether they need to show up and whether they need to make alternative choices to get to their destination. And IoT is super fascinating. You think that trains really don't need IoT, but there's lots of cool little things that can talk to trains, and they might be, simple things like sensors, track monitors alerting whether a switch is in a certain position, alerting to speed limits and things like that. But also some very interesting high-tech things like the usage of drones, and we'll drive into that a little deeper in a second. But autonomous trains are really, a big thing. We've seen it in cars. We've seen it to some degree in planes for decades now. but letting the train drive itself efficiently, reducing labor costs, improving safety, and finding ways. Now, that the nice thing about trains is you don't have to think about steering, but you do have to think about braking, whether the track is safe, whether the speed is safe for the particular track and the environmental conditions, whether people have gotten on the train or off the train and they're clear of the train, but is it safe to start? Is it safe to stop? Is it safe to proceed? So some interesting things. Predictive maintenance is one of those fascinating areas where automation helps, because as we start to analyze the wear of parts, we look at brakes, we look at wheels, we look at gears, we look at sensors themselves, and we can start to recognize when things need to get replaced, either because typically they last so many hours or so many miles, or because we're actually seeing symptoms through sensors of increased friction, for example, so that we know that we need to replace parts. And so it can save downtime. The cost of the replacement parts doesn't change, but the fact that we can plan the maintenance and not impact schedules is extremely important. And the changing role of human operators. We don't want to replace everybody with machines. That's nuts. Okay, what we want to do is make people more effective at their job by empowering them and enabling them with more information about what they're doing, all at their fingertips. So automation is extremely important to rail industry. Big data, yeah, collecting data about the trains. You've all seen, I'm sure, dashboards of rail control centers, and it's always fascinating for me to watch and see all the different things on the different tracks when you think about how many individual pieces are in motion at any given moment in a rail system. So having big data helps us optimize operations so that we can make sure we're not delayed somewhere, waiting, held up, waiting for a train to move out of the way, but also improving safety, again, making sure that we don't put two trains in the same place at the same time, and that we're looking out for symbols and symptoms that would identify imminent breakdowns, such as overheating brake systems or failing brake systems. And again, enhancing the customer experience. Are people happy? Are they taking the same ride? Are they getting off early? Are they going to the destination? Do they always take a 9 o'clock train but never a 10 o'clock train? All kinds of things that you can do with big data. Internet of Things, of course, smart trains, right? We get sensors, we get real-time data analysis, so the train starts to really understand, not just where I'm at and how am I doing, but how's everybody else doing? What's up ahead of me? Is there a slowdown at the next station, and can I move a little slower so that we don't have time sitting somewhere? Or as I see passengers diving on and off, can I give them another minute or two since we're going to be stopped at the next station? All kinds of cool things that smart trains can do for us. And that, ties in with the connected infrastructure. IoT enabled connected infrastructure with track switches so that we can optimize, you know, routing, we can optimize traffic wait time, reduce downtime, increase capacity, and the drones, right? And I had the drones as a highlight there, but drones are being used for inspecting rail infrastructure. We look at tracks, bridges, tunnels, make sure they're safe. In bad weather, we can see how clear they are. In the case of a storm, we can see if a tree is falling across the tracks. We can also do manual inspection on dangerous or hard to reach areas. Like you're trying to inspect the tracks or the underside of a bridge over a nasty, gorge. You can do that with the drone. So it's pretty interesting because it gives us the ability to move very quickly, and we don't have to, drive a vehicle onto the tracks to do the track inspection, at least not all of the time. So it can make things much easier with a much lower impact on the system. So in summary, what we're seeing in the rail industry is a push to be safer, right? And finding ways to make things safer through better automation, better software, and use of IoT. And again, a push to make things more efficient. We always need to get more people on the train. We need to get higher usage of every particular train, make sure that the cargo's all there, all the people are there, that we're maximizing dollars so that we can afford to keep the trains going. And a lot more use of things, the Internet of Things, right? Devices, drones, remote switches, local switches, dashboard displays, all kinds of cool stuff. And all of this obviously brings more software. And again, we've seen this in other industries. Software has exploded not by a factor of 10, but by a factor of 100 or even 1,000. And so more software brings a lot more interesting capabilities, greater automation, greater efficiency, but also brings challenges in software testing to make sure that as we're adding features and capabilities, that we're continuing to operate in a safe manner. So I hope that's interesting for you all. It's a very interesting time in the rail industry. Lots of cool stuff that you can look up. And with that, I'll hand it back to you, Ricardo.
Thank you, Arthur. Amazing transformation that the rail industry is going through. Okay, let's now dive into the software development standards for rail in support of this evolution. The EN5012X series is a set of European standards that define the safety requirements for railway applications. This series provides guidance on various aspects of railway systems, including signaling or protocols used to control and manage train movements. And this is for all rolling stock, which means freight cars, passenger cars, the locomotive, and communication systems. All these aspects of rail with a focus on ensuring functional safety, reliability, and performance. Now, EN50126 provides the general guidelines for achieving and demonstrating reliability, availability, maintainability, and safety. You may have heard the term RAMs. It's the overarching standard that sets the framework for EN50128 and 50129. Now, jumping over to EN50129, this standard puts emphasis on the evidence needed to demonstrate safety for the train signaling device, which is what performs railroad monitoring and control. And the other aspects of the standard is on risk assessment and safety integrity levels, SIL, which I'm actually sure you're all very familiar with. Then there is EN50128, which focuses on the software development and use in rail control and protection systems. It details methods for software development and testing or validation. It is also important to mention standard EN50657. It complements EN50128 by focusing on requirements for software and rolling stock applications to help ensure safety and reliability. However, there is now a new standard, EN50716, that was released November of 2023, which combines, supersedes, and replaces both EN50128 and EN50657. EN50716 lays out a very clear development roadmap. You see the infographic that they have provided on the right-hand side of this slide. There are 9 sections. Section 1 sets the scope of the document, which specifies the process and technical requirements for the development of software. Section 2 lists the normative references, which there are none. This means that regarding the requirements for software development, EN50716 is the one to follow. And Section 3 contains the terms and definitions of the standard. Now, I'm going to quickly take you through each of these sections, but it's very important to remind you that you still need to adhere to supporting standards like EN 50126 and 50129. There are also many other supporting standards that add value and organizations have adopted. For example, IEC 62443 for integrating security into the development process. There's also the FRESH TS 50701 standard on cybersecurity. In fact, that may be a good standard for Arthur and I to present on the near future. There's also IEC 60050 on risk assessment, or ISO 9001 on quality management, and the list continues. Let's now go to section 4 of this standard. Section 4 focuses on software integrity requirements. It defines 5 levels of software integrity. SIL 0, which is not shown in the table. You have the basic integrity, SIL 1, the lowest, to SIL 4, the highest. The appropriate level is determined by assessing both the system's safety and the risk involved in using the software. This is done through performing a failure mode and effects analysis And you see that I've listed various other techniques you can use. To give you a very quick understanding, you need to analyze and determine the safety integrity level of software components by asking and answering questions such as what could go wrong, why would the failure happen, and assign values to metrics like severity, occurrence, detection, or controllability. Then, based on a multiplication result and a determined result range, you then make the SIL assignment. Also, know that when selecting these techniques and measures, Annex A provides guidance, and these decisions must be documented in the software quality assurance plan. And if you deviate from highly recommended techniques, you will need to document the rationale. Lastly, software developed according to EN 50128 or EN 50657 remains compliant and can still be used for new projects. So this standard does not invalidate that software. Okay, so the main focus of Section 5 is on how you organize and manage the people working on software projects. The goal is to make sure that everyone has a clear and independent role to reduce the chances of mistakes and avoid any conflicts of interest, especially when it comes to making decisions about safety. You need to make sure everyone in their respective roles has the right qualifications, training, and experience. It's also crucial to keep track of their ongoing development to continue to meet the required quality standards. On the documentation side, you need to structure the software development process into clear phases and keep detailed records. What's nice about this standard is that it lists all 47 documents needed for your project. In addition, you need to pick a lifecycle model for software development and make sure that quality assurance procedures are aligned with this model. In short, it's all about having a clear structure, ensuring everyone is qualified and independent, and keeping detailed and consistent records to ensure smooth and effective software development. If you are already applying these practices and are very familiar with quality management standard ISO 9001, many of these requirements are probably already being met by your organization. Now, Section 6 outlines how to manage software assurance for safety critical systems. It's about process and what is expected. It breaks down the process of software testing, verification, validation, quality assurance, and assessment into clear steps to help ensure that the software behaves as expected and meets all the safety requirements. For software testing, the goal is to confirm that the software behaves according to its specifications. Be aware that integration testing between software and hardware is a key part of this process. Now, software verification is a bit different. It's more about checking if the software meets the requirements and design specifications. This is done through a software verification plan that details how the system will be verified, along with reports to track progress. For example, gaps in your requirements traceability matrix helps verify your requirements. Now, software validation is where we check if the software is actually fit for its intended use. The focus is on whether it meets all functional requirements and safety standards, with a validation plan and report documenting the activities. Then there's software assessment, which is carried out by an independent assessor. Their job is to ensure that the software complies with all required safety integrity levels and meets the system's intended use. The results are documented in an assessor's plant report. Section 6.5 on software quality assurance ensures that the entire software development process maintains high standards. This includes managing documentation responsibilities and ensuring every change or modification goes through a structured process, all overseen by a configuration management. Finally, regarding support tools and languages, the focus is on ensuring that these tools do not negatively impact the software safety and integrity. The tools used should be selected based on their suitability and with documented evidence of their reliability. For example, Parasoft C and C++ testing tools satisfy this criteria. Not only are they certified by TÜV-SÜD, but they have a long history of being used in the development and testing of software critical systems. Section 7 on software development is the core of this standard. You're all probably very familiar with the V model. It is used to express the different phases of the life cycle. On the left-hand side, you have different development phases, and on the right-hand side, you have the testing phases, which they coincide with each other. So look at each phase horizontally because development and testing are tied hand in hand. And just to clarify, the V model is not a software development methodology. It's a way to convey the recommended development phases and processes by the standard. Section 7.1 expresses the need to choose a software development methodology. The standard introduces new guidance, particularly on adopting and executing an iterative development methodology. It is up to your organization to choose the methodology that best fits the project. However, in some cases, I've seen stakeholders dictate the development methodology. The common ones are the waterfall, spiral, and agile. In addition, there will be lots of paper artifacts that need to be produced. Each of these subsections that we will go through, I'll list the documents that need to be authored or enhanced. Part of the benefit is that these documents produced are an actual audit trail as required by the standard. Section 7.2 on the software requirements entails gathering system requirements, information on the architecture, and quality assurance plans. This information will guide the creation of the software requirements specification and the overall software test specification, which are key documents needed. The software requirements specification must clearly describe all the important aspects of the software, including its functionality, performance, safety, and how it interfaces with other systems. It also needs to identify and document all hardware and software interfaces, modes of operation, and safety-related behaviors, including how the software handles failures. Once the requirements are written, a software test specification will describe how to test the software, including inputs, outputs, and the criteria for success. Finally, a requirements verification report will confirm that the requirements are complete, traceable, and consistent. A requirements traceability matrix is a common artifact used to identify gaps and verification of requirements. Requirements are commonly captured in an ALM or requirements management tool like Polarian, JAMA, Codebeamer, and each requirement must trace to the test case that validates it. So know that Parasoft testing solutions integrate with many requirement management tools to satisfy the verification and validation of all requirements and automates traceability to the test cases. Section 7.3 on architecture and design covers the key steps in designing and architecting the software. You need to identify all the software components and their SIL levels. You need to make sure that the architecture is not too complex and it has clear data flow and supports fault detection. The standard also offers requirements around handling pre-existing software. It also needs to be validated to its determined SIL level. There are also 6 document artifacts to produce, and you can see them listed here. And finally, you will be needing to integrate these components together, so you will need to perform integration testing to ensure the software components work together as expected. And also that the software and hardware interact safely when integrated together. Section 7.4 Component Design focuses on how to properly develop and test software components. First, there are 2 main objectives. One is to develop a detailed design for each software component, and the second is to create a test plan for each component to make sure it works as expected. When you start, you'll use the software design specification as your main input document. From there, you're going to produce 3 main outputs: a software component design specification, a test specification, and a design verification report. For each component, you need to write a detailed design specification. It will break down each component into its smaller parts, like methods or functions, and specify how these parts interact with other components. And the design should be clear, consistent, and ready to be transformed into code. Once the design is written, you need to make sure that it's testable. You'll create a component test specification that outlines how the component will be tested. Later in this presentation, I have some slides with tables showing testing requirements based on the SIL levels. In short, the process ensures that each component is carefully designed and thoroughly tested. At this phase, unit testing is what will be performed, and I would actually include code coverage. Also, make sure to document your results to produce your verification report. Section 7.5, the component implementation and testing phase, focuses on making sure the software is written so that it's easy to analyze, test, verify, and maintain. The process starts with two key inputs from the previous phase, the software component design specification and the software component test specification. They guide how the software is developed and how it will be tested. Now, in terms of what's required, the source code needs to be well structured, balancing complexity, maintainability, portability, and easy to read. I strongly recommend applying static analysis as you implement the code to achieve these best practices. In ensuring actually you have great code quality and safety, reliability and security, maintainability and portability. Then the test report created by the tester must show whether the component meets the design requirements and whether the necessary test coverage was achieved. Finally, the verification report written by the verifier checks that the source code implements the design correctly, that it follows coding standards, and that the tests were sound and valid. To recap, the entire phase ensures that the software is properly implemented, tested, and documented. Note that we are also starting to move up the right-hand side of the V model there. In the integration phase, the goal is to combine software components and ensure they work together properly, as well as verify that the software interacts correctly with the hardware. The process starts with documents like the software hardware integration test specification and the actual source code. After testing, three key reports are produced: the software integration test report, the software hardware integration test report, and the software integration verification report. The idea is to make sure all the interfaces work well before moving to the larger system integration that follows. Also, if any requirement changes happen during the software hardware integration, there has to be an impact study to see which parts of the system are affected, and then those parts need to be tested again. Again, the requirements traceability matrix is fantastic for this. Then if you iterate through this, you will need to perform regression testing besides integration testing and testing on the actual target hardware. When you reach section 7.7, the overall software testing and final validation phase, what you're doing is making sure that the software and hardware together meet all the system level requirements outlined in the software requirements specification. Here's how it plays out. You perform system level testing, which involves either real hardware or simulated environments to mimic actual operating conditions. Produce your software validation report from test results to confirm that the software meets its objectives. Then produce your release note document, which includes important information on hardware compatibility and any limitations. Any discrepancies identified during testing need to be tracked and addressed, ensuring everything is fixed and ready for final release. Now, before I forget to mention, in these tables, you will see the SIL level and below them, the recommendations. You have M for mandatory, HR for highly recommended, R for recommended, and a single hyphen means no recommendation. EN 50716 elaborates more on these testing methods, so I'm going to quickly cover the key ones. Static analysis is primarily a method of finding implementation issues by analyzing the source code without having to execute it. There is the term shift left, and static analysis is the prime example of shifting left software testing. And why this is important is because developers can address these identified bugs or coding issues before they become more complex and costly to fix later on in the software development lifecycle. It's just commonly known as a truth that fixing bugs during the early stages of development is significantly cheaper than resolving them later on in the lifecycle or post-deployment. In support of this, you have industry safety coding standards like MISRA, AUTOSAR C++14, High Integrity C++, and many other. In fact, you may have your own homegrown coding standard. What I'd like to convey is that Parasoft's static analysis solutions fully supports all the rules in these standards, and you can customize it to support your own homegrown coding standards. We also support security coding standards like CERT, CWE, and cybersecurity standards like OWASP, DCISD, STIG, and others. I'd also like to add that our static analysis provides other valuable insights into your code's quality metrics like complexity, readability, testability, maintainability, and which many of these are recommended by EN 50716. And as a byproduct, it actually teaches developers good coding practices. It makes them better software developers. The EN 50716 standard calls for dynamic analysis, and that includes a lot of test methods performed through code execution. You have unit, integration, system, regression, on-target testing, and many more. We have various testing solutions, particularly for C and C++. We offer a comprehensive unit testing framework that provides teams with seamless test creation, execution, and regression capabilities. Easy to use features, which includes mocks, stops, and assertions to effectively perform unit and integration testing. We also include automated test reporting, which aids in satisfying compliance demands, while our web-based dashboards are interactive and provide integrations with other solutions in requirements traceability, defect tracking, and we even use AI/ML for our prioritization of static analysis violation findings. And there is much more like incorporating test coverage, so let's talk about test coverage. EN 50716 specifies various structural code coverage metric recommendations, which we support all of them. And our generated reports detail each line of the code's execution status, whether it's fully, partially, or not covered. And these auto-generated reports and dashboards serve as critical reference for testers and certification auditors. They seamlessly facilitate the assessment of code coverage compliance. Parasoft also automates linking requirements from various ALM solutions like JAMA, Codebeamer, Jira, and others to test cases that satisfy them. This ensures comprehensive verification and validation. It provides clear bidirectional traceability, ensures quality by verifying that functionality matches the requirement, and our traceability supports the mandatory compliance demand defined in EN 50716, as you can see in the table. Traceability also builds stakeholder confidence by demonstrating thorough and focused testing aligned with all specified requirements. All right, so this section 8 is all about how railway systems are customized for specific installations using what's called application data. The idea is that you need to have a standard piece of software, but you need to customize it to meet the unique needs of each setup. Like the signaling system or door controls in a train station, the key component is the application preparation plan, which outlines all the activities, tools, and safety checks needed. It ensures that the customization process is safe, tested, and verified. Also, make sure that the release document explains how the system should operate, its compatibility, and any restrictions. In short, the process ensures that the system is safely customized, thoroughly tested, and well documented for future use. Section 9 on software deployment and maintenance aims to ensure the software maintains integrity and reliability in its deployed environment. There will be a deployment manual, and the project manager will oversee the deployment. For software maintenance, the focus is on preserving software performance during updates or fixes. Maintenance is planned with strict control over changes, and these changes will be categorized as major or minor, and a change record will be maintained to ensure integrity of the system. Okay, now in Annex C of the standard is where you will clearly find new additions and guidance that is provided by the standard. EN 50716 expands on development lifecycle models, particularly in iterative lifecycle models where you repeat certain phases multiple times, breaking the project into smaller chunks. So instead of doing everything in a single linear process like the waterfall, you do it in cycles. Each cycle or iteration refines software requirements, designs, tests, and integrates components. Now, EN 50716 also clarifies and expands on the use of modeling. Modeling languages like the Unified Modeling Language and the System Modeling Language, so UML and SysML, they are both very powerful tools that can help manage complexity by abstracting implementation, design, and system details to higher levels of representation, thereby enabling clear understanding, effective communication, and better management of software and systems engineering projects. To give you an analogy as a software engineer, modeling is like moving from programming in assembly language to programming in C++. Finally, EN 50716 provides some minimal guidance on artificial intelligence. Machine learning is increasingly relevant, but the standard presents only the challenges in AI and compares them to traditional software. For example, machine learning relies on training data, making verification very difficult because the output or results don't trace nicely like they do when you're decomposing requirements in the traditional approach. The main challenges with machine learning include ensuring that the training data is complete, verifying the software is trained, validating the model's functionality, and dealing with adversarial attacks. Right now, the authors of the standard are continuing their ongoing research to tackle these problems, but the standard does not yet have widely accepted best practices for using AI or ML. What I'd like to add is that AI models can be frozen so that they become deterministic, which helps solve a lot of these presented challenges. I recommend looking at other industries like automotive and medical devices for inspiration on adopting AI. I also like to quickly touch on iterative development and our powerful solutions in this space. Unlike conventional testing tools, Parasoft offers seamless integration into developers' desktop environments and modern iterative development workflows. We offer solutions that run within IDEs like Visual Studio, Eclipse, Eclipse-based IDEs, VS Code, and many others. But we also offer solutions that you can plug right into your continuous integration pipeline. They have intuitive command line interfaces. There is no IDE dependency, so it makes them very versatile and adaptable to any existing development ecosystem. For example, our product, CC++ Test CT, seamlessly integrates with open source unit testing frameworks such as Google Test, Boost Test, and CPP Unit. So if you are already using these test solutions today, we can enhance them by adding test code coverage, requirements traceability, and automated compliance reporting on top of them. To put Parasoft in full context, we offer end-to-end testing solutions for Rail. Parasoft covers all your needs with a dedicated automated testing solution for each step in both the verification and validation stages so you can achieve compliance and deliver safe, secure, and reliable software. The V model illustrates how Parasoft solutions integrate into your development process. Anyways, this concludes the presentation on EN 50716. I hope you found it very educational. And I think I hand it back to you, Arthur, for Q&A. Forgot to unmute myself. But actually, before we go on this Q&A, I put some QR codes on the slide where you can tour our C and C++ testing automation solutions. It's really cool to kind of go through that simulation. Also, there is on the far left, if you want to request a custom in-depth demo, it'll take you to our website where you can will help you fill out a form and you can provide that. So it's really nice. Also, visit our website. We've got tons of content. We have previous webinars that Arthur and I have done, and lots of rich stuff. So please do that. Also, don't forget to follow us on LinkedIn, Facebook, Twitter. And if you happen to have any questions after the webinar, please send it to us at info@parasoft.com. All right, so we've opened it up for Q&A. Just have a few questions here. Um, how does EN 50716 guide the testing and integration of railway software with hardware components? So yeah, there can be a little confusion on integration testing. There are two phases in EN 50716 that emphasize the importance of integration testing to ensure that the software components interact correctly with each other. And that was 7.5. So this is a software component integrated with another software component. So this entails unit testing, integration testing, regression testing, and any APIs components between them, or interfaces between them. Now, 7.6, the software integration phase, focuses really more on the hardware and software integration. Here you will be testing that software and the real target, or also, as they stipulate, simulated hardware environment is also acceptable. So you can form these things like regression testing, integration testing, again, APIs, part of system testing, and all the test results need to be documented. So we have one other question here. What guidance does EN 50716 provide for handling pre-existing software components in the new railway projects? Yeah, so the standard allows for the use of pre-existing software components. However, it needs to go through the validation process, and it must demonstrate that it meets the system's requirements. So the requirements for the pre-existing component need to be captured. They also need to be traceable. So as you decompose your system, and the component needs to go through the entire verification validation process. Also, if the pre-existing software integrity level happens to be at level 3 or 4, you actually have to do a new failure analysis. So that needs to be performed. So that altogether, this is going to ensure that the system, that component, that software is safe and will work as expected within the system that's on design. Okay, so we only have just one more question. What coding standards are recommended by EN 50716 and how are they applied? So the standard does not recommend any particular coding standard. It only recommends that you apply coding standards to ensure that there's good programming practices and you deliver quality code. And that the standard help you address code metrics. They mentioned, if you heard me talk about complexity and portability and so forth. Now, I personally recommend coding standards like MISRA, and you can complement MISRA with CERT for security. That's a lot of folks do that. As you probably know, MISRA was updated last year, so you have a very current coding standard for today's embedded development. And I will recommend that you, of course, use Parasoft to apply it, not only because we fully support the entire standard, the rules and guidelines, but because we integrate it within your IDE, making it very easy for engineers as they're coding. And we also can integrate it within your CI pipeline. So this, again, helps support modern iterative development workflows. All right, folks, well, we don't have any other questions. Thank you very much for attending. Thank you, Arthur. That was fantastic.
Yeah. Thanks,
And
Ricardo. It was fun to join you, and for everybody who's here, thanks for coming. And if you haven't done it lately, go out and ride a train.
thank you, everybody. Have a great rest of the day. Bye-bye.
Bye.